All right, welcome back, everybody. Okay, so today we're going to continue talking about vector calculus. So this is like divergence, gradient, curl. Today what I really want to talk about are integral theorems. So we're going to talk about Gauss's divergence theorem today. And so it's kind of a neat, extremely neat theorem, Gauss's theorem, but it's also the basis for a lot of the partial differential equations that we're going to see in the following quarter. Okay, so something kind of interesting that we'll get to today is that a lot of PDEs can actually be derived through conservation laws. And conservation laws usually mean I do some accounting over a volume, meaning I integrate some quantity over a volume, and I see how much it changes and how much of that quantity leaves the volume. Okay? And using this kind of integral approach to conservation laws is how we usually derive lots and lots of partial differential equations. Okay? There is a chance this will be a bit of a short lecture, but we'll see. Okay. Okay, so just the topics. Overview of topics. So first we're going to talk just very briefly about double and triple integrals. Triple doesn't have two p's. Okay, then we're going to talk about Gauss's divergence theorem. I'll give you an example that's pretty close to the example I gave on the qualifying exam this last week. So actually, I think that the example on your homework set is the problem from the qualifying exams. Wasn't that creative this week. And then we're going to talk about how Gauss's theorem can be used for mass conservation, so the continuity equation. Okay. Before I start, are there any questions about anything in the class so far? The last few weeks, the next few weeks, finals, differential equations, anything? Okay, so I mean, it kind of feels like the class is winding down because this is the last week, and then, well, this isn't the last week. This is, I'll give 3 lectures this week, then I'll be gone all of next week, and then we'll have 3 more final lectures in December. And so these next 2 weeks are really kind of a catch-all for things that you certainly should know for the next part, PDEs, but most of you probably already do know. Okay, so I'm assuming that most of you have seen Gauss's theorem and know how to do double and triple integrals. And in fact, with double and triple integrals, I'm going to do one example today of a volumetric integral, but I'm going to assume that you actually know how to do compute areas and volumes and things. So if you need to do a little bit of a review, then Chapter 9 in Kreisig is actually pretty good. And there's a number of ways that you can get access to this book. Juan Risa has desk copies in her office. So I'm going to really gloss over double and triple integrals really quickly, and I'm going to get to the interesting things that you can do with these double and triple integrals. Okay? So really, I'm going to start with Gauss's theorem. Okay, so just a quick show of hands. How many of you have seen Gauss's theorem before? How many have not? Okay, how many of you could use Gauss's theorem to compute an integral right now? Probably a few of you have started the homework. Okay, good. Okay, so Gauss's divergence theorem is probably my favorite theorem in vector calculus. It's not everyone's favorite theorem. I know some people are partial to Stokes' theorem, but I think this is a really, really good one. So I'm going to say it in words first, and then I'm going to say it in math. Okay, so in words, Gauss's divergence theorem has to do with the flux of quantities through a volume, okay, or through a surface. So the flux of a vector field out of a closed surface Okay, so I'm going to do it in words, then in math, and then in picture. So the flux of a vector field out of a closed surface is equal to the integral of the divergence of the vector field over the whole volume. Okay. I'm going to draw a picture, and then I'm going to write this in math. Okay. So let's say that I have some volume, and I have some vector field that's going on in the background, like I have my velocity field or something like that. So the way I always think about this is that I have some vector field like a fluid, and I have some volume of fluid that I'm going to be studying. Okay, maybe this is a small, teeny tiny little packet of fluid in my coffee cup when I drop cream in. Maybe this is a 5 square mile swath of oil in the Gulf of Mexico. Maybe this is the entire trace of the Fukushima radiation plume in the Pacific. Anyway, this is a volume in a vector field. Okay? So we have space. We have some vector field in space, and I'm going to study some volume in space. Okay? So let's call this volume V. And we're going to call the surface of the volume, so the surface of this volume that I've carved out in space, we're going to use this symbol partial V. And this is a commonly accepted kind of mathematical language. Partial V means the boundary of my volume, the surface enclosing my volume. Okay? This actually has good reason to use partial, like partial derivative, because of the way that Stokes' theorem works. We'll see that later. And then finally, we're going to have some normal vector pointing out of the surface. Okay? So what I want to know is how much stuff is this vector field taking out of my volume or carrying into my volume? That's what flux means. Super simple concept. The flux of my vector field just means how much stuff is being carried in or out of my volume. Okay? Is this volume accumulating mass? Is it losing mass? Or is the mass basically staying the same? Okay? And we can write this in math in the following way. Okay, so the first quantity that we're interested in is this flux of my vector field out of a closed surface. So that's equal to a double integral on the boundary of my volume of my vector field dotted in the normal direction. Okay? So if I was going to keep track, let's say I built a fence around Seattle and I wanted to keep track of who came in and who came out. All I would have to do is count how many people go out and how many people come in. Right? So that means I'm going to integrate around the surface of my volume, the boundary of my volume, and I'm going to figure out how much of my vector field points out, and I'm going to add up all of that outward or inward contribution. Okay? And this is a fine integral, but it's kind of a pain to represent this surface and find some way to parameterize, and it might be really, really hard to integrate some vector field over a really nasty, ill-defined surface. And what Gauss's theorem says is that instead we can do this triple volume integral over the entire volume of the divergence of F over the whole volume. Now, this might not look like we actually made anything easier because we went from a double integral to a triple integral. Usually that's a bad thing. But oftentimes when you take the divergence of F, this vector field divergence is much, much simpler than F itself. Okay? So for incompressible fluid flows, this is 0 everywhere in all of space. Okay, so are there questions about what this kind of means physically or geometrically? How many of you would like me to say kind of what this means physically one more time? Yeah, okay. Okay, so just one more time. This is a super important theorem. The idea is oftentimes I'm interested in whether or not a quantity is conserved, like is mass being conserved in this volume, or where will oil go if it spills, right? We know that the volume of oil is going to be conserved. And so sometimes I will create this control volume, and I'll want to keep good accounting of how much stuff is in this control volume, how much oil is in there, how much nuclear waste, whatever. And to do that, I need to know how much of that stuff is coming in and how much of that stuff is going out. Right? I want to know like the rate of change of the quantities in this volume. And so what I'm going to do is I'm going to take my vector field, and if my vector field is perfectly tangent to my surface, then that part of the vector field is not driving particles in or out. But if my vector field is pointing partially outward, then when I take the dot product of f with my normal vector, some portion of that vector field is carrying particles out or taking particles into this volume. So this integral here, this integral of my vector field dotted with the normal, integrated up over my entire boundary, is the flux integral, or flux of mass through partial v. Okay? And Gauss's theorem says that this always equals the volume integral of the divergence of f. There are some really, really cool proofs for this, and part of me really wants to show you why this is true, but a bigger part of me thinks that you've probably seen it before, and it's probably not going to make a huge difference. But if you are interested, there's some great reasons why this is true, kind of intuitively and geometrically. You can get a sense for why this divergence theorem is true. Okay, so let's do a really, really simple example. And this is an example that's almost exactly like the problem on your homework and on the qualifying exam. Okay. So what we're going to do as our example is we're going to take a sphere in x, y, and z. Okay, so we're going to take the sphere, and we're going to integrate the flux of a certain vector field out of this sphere. Okay, so we're going to let our vector field f equal 2xi plus y squared j plus z squared k. Okay. This doesn't have any physical meaning. I just made up a vector field that had some nice properties. And so this vector field f gives me a direction at every point x, y, and z. Right? It's a vector field, kind of like in our ODEs. And what we want to know is how much of that vector field is carrying mass out of the sphere versus into the sphere. What is the net flux of things in or out of the sphere? Okay? And we're going to say that this sphere is given by the set of points x, y, and z such that x squared plus y squared plus z squared equals 1. Okay. Okay, so on the quals, you might have a problem like this. You might have a sphere and some vector field, and you're supposed to compute the flux of that vector field through the volume of the sphere. Okay? So compute flux through S. Okay, this is a great classic divergence theorem problem, because if I wanted to integrate this f across this surface, I certainly could. I could say that's the integral of S of f dot my normal vector ds. That's the flux through my sphere of this vector field. But this is going to be super nasty. Right? Like f is this nasty function. I'm going to have to find out what my normal vector is, dot it, and do this weird integral over this surface, which is not easily parameterized by x and y. Okay, so it's kind of a pain to do this integral. But Gauss's divergence theorem makes this really, really easy. So this is equal to the integral of my volume of the divergence of f. So how do I compute the divergence of f? What is the divergence of f here? Right, I take all of the partials, partial this partial x, plus partial this partial y, plus partial this partial z. Okay? And I get div f equals 2 plus 2y plus 2z, right? Okay, so at any point, x, y, and z, at any point, the flow is diverging or converging in this amount. And we could take this vector field and we could create a mesh grid of particles in MATLAB, and we could actually plot all of those vectors for a mesh grid and see that some places they're expanding, some places they're converging. Okay? Okay, so we have to compute this volume of this quantity. So we're computing the volume integral of 2 plus 2y plus 2z dv. And there's something really cool we can do here. I'm going to split this into 3 integrals. Right? Integration is also a linear operator, so integral of a plus b plus c is the same as integral of a plus integral of b plus integral of c. So this equals, I'm going to drop the triple integral because I'm sick of writing it, integral volume of 2 dv plus integral volume of 2y dv plus integral volume of 2z dv. Okay. The first term, pretty simple. What is the volume of a sphere? 4/3 pi r cubed. R is 1, so it's just 4/3 pi. So this equals 8/3 pi, that term. Okay, what about my other 2 terms? If I want to integrate y over the volume of a sphere, what do I get? So I'm going to go through every single point in this sphere, and I'm going to add up y, and I'm going to get what? Okay, I heard 1 and 6. Any other? 0 sounds good. Why would you say 0? Because it's symmetric. There is as much positive y in the upper hemisphere as there is negative y in the lower hemisphere. Okay, so for every point that I add up, sorry, upper is z. So for every point positive z, there's a point negative z, and those add up to 0. So my integral of z over the volume is 0, and similarly my integral of y is symmetric and equals 0. Does that make sense to everyone why this integral has to be 0? Because there's as much positive y as negative y. This is a symmetric surface. As a general rule on qualifying exams, I will almost certainly never give you an integral that doesn't have some kind of a symmetry, because I hate doing nasty integrals. So these are both 0, and this is my answer. Okay, so this is a classic example of a problem that is easy to do using Gauss's divergence theorem. I took this nasty vector field, integrated over some surface that's hard to parameterize, but it turns out that the divergence of this vector field is easy to integrate over the volume. Okay, so this is the amount of flux through that sphere. You could imagine that these vector fields came about through some physics problem, right? I wrote down some, maybe I have some distribution of charges inside of this sphere that are creating that vector field. Or I have some kind of gravitational potentials that's creating this vector field. So in reality, these F's that we're going to be integrating are going to be physical vector fields, like gravitational potentials, or Coulomb charge distribution, electrostatic potentials, and things like that. Okay, any questions about the kind of mechanics of what we did here with the integral? So you can verify at home that this surface integral is way, way harder than this volume integral. Just like try to do it, and it's kind of a pain. Okay? Okay, so I will do one more example that is even closer to the qualifying exam. So I figure no one would mind hearing how to solve a homework problem, right? How many of you have started this homework problem yet? Okay, yeah, so I'm going to make it a little bit easier. Okay, so in the homework, we are integrating essentially an exponentially growing parabolic dish. We're finding the volume under that dish, and then we're creating the flux integral outside of that volume. Okay? So I'm going to make a slightly simpler version of this problem where we have some surface f of x and y equals x squared plus y squared. Okay? And in x, y, and z, this just looks like a parabolic dish. Okay? And what we're going to be doing is we're going to find the volume under this curve. So find volume under f of xy for x squared plus y squared greater than or equal to 0, less than or equal to 3. This is very, very, very similar to the homework problem. And so the idea is I draw this kind of circle here of radius r equals square root of 3. And I want the volume of everything under my parabolic dish above this xy plane inside of this radius root 3 circle. Okay, so it's this weird looking like cylinder with a paraboloid cut out of it. That's what I want the volume of. I want the volume of this cylinder with this paraboloid cut out of it. Okay? Now, anytime you see something symmetric, you can probably make the problem a lot simpler. So this is the same as 0 less than or equal to r squared less than or equal to 3. So I'm going to use radial coordinates. And I'm going to integrate this volume using nested cylindrical shells, like Russian nesting dolls. Okay? How many of you remember doing integrals with cylindrical shells, just adding up shells of cylinders? Okay, this is one of my favorite types of integrals that I still remember how to do. Okay, so we're going to basically be adding up all of these cylindrical shells. So okay, so we're going to add up all of these cylindrical shells where the height of the shell is given by this paraboloid f of r equals r squared. Okay? All right, so we have the volume here equals, the volume is some triple integral of dv. And so we're going to integrate with respect to radius, theta, and height. Okay, this is a triple integral, so I'm going to use cylindrical coordinates. I'm going to integrate from radius equals 0 to root 3, from theta equals 0 to 2 pi, and from z equals 0 to f of r. That's just a fancy way of saying for each radius between 0 and root 3, I'm going to take a cylindrical shell of height f of r. Okay, and this is dz, d theta, dr. Okay, so what's the integral of dz? Z. Okay, so I get, I'm going slow here because this is probably the last example I'm going to do of a real triple integral. So the integral of dz is just z, and if I evaluate that at f of r and then at 0, I just get f of r, which is r squared. Okay. The thickness of each of these little cylindrical shells is dr. Okay, so the volume is going to be r squared times 2 pi times dr. Okay, integral of theta, d theta is just theta, so we get 2 pi r squared dr. Okay, this is the formula for cylindrical shells that most of you wish I had just jumped to. Right? Any cylindrical shell has a volume 2 pi times the height, which here is radius squared, times dr. Okay, this is just the formula for a cylindrical shell. This is 2 pi h delta r, if you like. Okay, that's the volume of a very, very, very thin cylinder of height h. And so finally, I can integrate this with respect to r, and I get r cubed over 3 times 2 pi, evaluated at root 3 and 0. And this is pretty straightforward. So root 3 to the third power is 3 root 3. And I'm dividing by 3, so I get 2 pi root 3. Okay, so that's the volume of this weird paraboloid-looking thing. You could have just jumped right to here and said, OK, I'm going to use cylindrical shells. Those cylindrical shells have height f of r, which is r squared. And I'm integrating from r equals 0 to root 3. OK, so this is, you know, the homework problem is a little bit more complicated because it's e to the r squared. OK, but there was a second part of this homework. And that second part was to compute the flux through the surface bounding this volume of a given vector field that I chose. So let's say that I have a vector field, big F equals 3x minus 2xy in the I direction, minus y in the j direction, plus 2yz in the k direction. Okay, so this vector field could be the right-hand side of a differential equation. Is it pretty clear how this could be the right-hand side of a differential equation? Right? I could have like x dot y dot z dot equals 3x minus 2xy minus y 2yz. Like, this is a vector field, and it's just a different way of writing this vector field. Okay, vector field just means at every point in space there is a vector pointing in a direction. And so I should be able to integrate particles through that vector field using ODEs like we did in the first half of this quarter. So this is a vector field, and the part of it that lives in that weird cylinder with a paraboloid cut out of it, I want to know how much does that vector field carry particles in or out of that volume. Okay, I want to know what is the flux of this vector field through that surface. Okay, so again, we use Gauss's theorem. We say the double integral of my surface of f dot n ds is equal to the integral of my volume of div f. Okay, here the divergence of f is 3 minus 2y minus 1 plus 2y, right? partial x plus partial y plus partial z. My y's cancel, and I just get 2. So here I'm integrating 2 across my whole volume. So what is the answer then? Right, just 2 of my volume, right? I can pull the constant out, and I just get 2 of my volume, which should be 4 pi root 3. Now, it's not always the case that taking the divergence will make your life simpler, but oftentimes, especially for vector fields that are interesting from physics, like in gravitation or in electrostatics or in quantum mechanics, fluid mechanics, oftentimes the vector field that you get from physics, your life is a lot simpler when you try to integrate its divergence, because a lot of times the divergence is much, much simpler than the vector field itself. Okay? So there was a Russian guy around the same time of Gauss that also jointly invented this. His name starts with an O. It's Ostrogoretsky. I can't ever pronounce it. But really, we should be calling this the Gauss-Ostroh-something theorem. It would be nice to give him credit. OK. That's all I'm going to do in terms of examples of the divergence theorem. Are there any questions about anything that I did? So I feel like there might be a little bit of a mystery surrounding vector field. Like, we've been doing ordinary differential equations. That all makes good sense. We know that we have physics and they have things that change in time, and we want to follow those things that change in time. And we write down differential equations like we did there. When we move to vector calculus, I don't want us to have any mystery about what these vector fields F mean. Okay, these are just velocity fields from physics. It could be the field of all vectors pointing into Earth, indicating that Earth's gravity is pulling us in. It could be the vector field of repulsion between 2 positive charges. It could be the velocity field in the Gulf of Mexico that an oil slick experiences. Okay? These vector fields are just fields of vectors that I can integrate stuff through. Okay? They define differential equations and transport of quantities in that vector field. And what these integral equations, like Gauss's theorem, allow us to do is quantify how many particles will pass through a certain volume, how much mass will leave or enter a volume in a physical system. So this idea of using Gauss's divergence theorem for conservation laws is extremely important. So most of you are going to have some fundamental physics equation that you're going to be dealing with for the rest of your graduate career. At least this is usually the case, that there is some physical phenomenon that most people are studying, whether it's an elastic material or a laminate surface or a charge distribution or some quantum potential for a laser or a fluid flow field. But there is some governing equation that determines how that system is going to behave if you give it initial conditions and boundary conditions. Okay? And the whole study next quarter is going to be about those types of partial differential equation systems. So continuum surfaces and volumes that are changing over time. And we're going to start to see how we might derive these partial differential equations from conservation laws today. Okay? So mass conservation is probably the simplest example. So how many of you know about this continuity equation that I'm talking about? Right, this is the continuity equation from fluids, that the rate of change of the volume integral of the mass is equal to the divergence of the mass out of the volume. Okay, so most of you have seen it. And probably most of you, when you saw it, derived it from integral formulation. Most of the time. Okay, so that's what we're going to be doing. So we're going to consider a physical volume. I'm going to call it omega because V is going to be confusing. We have a volume omega containing some fluid. Let's say we're containing some mass, and that mass is a fluid. Okay, and we also have a velocity field. V arrow, okay? So this velocity field exists everywhere that the fluid exists, and it tells me where and what direction, how fast the fluid is moving, okay? So I have this volume omega. The boundary is called partial omega. I always have some normal vector pointing out of the surface. So surfaces are defined so that they have a normal sticking out of the surface. And I have some velocity field that exists in space. Some of that velocity field is passing through this volume. Okay, I have a fluid, and I'm zooming in on some piece of that fluid called omega. Okay, and we're going to say that rho is the density. Okay, so any change in the mass in this volume has to be due to mass either entering the volume or leaving the volume. Right? Aside from special relativity, there is no way for mass to be created or destroyed inside this volume. Right? We've known this for a long time. This is one of the most abundantly verified facts in all of physics, is that mass is conserved. So any change in mass in omega has to correspond to mass either coming in or out. Must correspond to mass being carried in or out by my velocity field V. Okay? Imagine I have a really, really boring velocity field, which is just a river, like a river going from left to right, and it's just constant velocity. Some of you are saying that rivers are not boring, but let's say you have a river going from left to right with constant velocity. Then the amount of mass in this imaginary volume that I've constructed should be conserved, right? The amount of mass coming in from the left is exactly equal to the amount of mass coming out to the right because I have a uniform velocity river. Okay, so that's kind of the simplest example that should get our intuition going, is if you just have a constant velocity field, then this flux should be zero, right? It's going to be the same in, same out. And so we're going to write this using Gauss's theorem. So we're going to say that any change in mass is ddt of a volume integral of rho d omega. Okay? So this is rate of change of mass. Okay, my volume integral of my density gives me the total mass. The rate of change of that volume is the rate of change of my mass. And this is equal to the flux out of the surface of rho v dot n d surface. So this is the way, I just said it in words. This is how we say it in math. The rate of change of mass in my volume is equal to, well, it's negative of the flux of mass out of that volume. If mass leaves my volume, I have a negative rate of change of mass in the volume. Make sense? Any mass that leaves the volume means that my total integral of mass in the volume is getting smaller. So mass out of the volume can only be carried by a vector field V that has some component pointing out of the surface in the normal direction. So I integrate over my surface V dot n, and those contributions carry my mass density rho out of the volume. Okay? So this is the mathematical statement of conservation of mass in an arbitrary volume omega. This doesn't just apply to fluids, but I have this vector field V that can carry me out of my volume. Okay, so now what we're going to do is take this integral, and using Gauss's theorem, we're going to turn it into a volume integral so that we can kind of relate these two volume integrals. Okay, so this volume integral of rho V dot n is equal to minus the triple integral over my omega of rho times the divergence of V over my volume. So from here to here, we just applied Gauss's theorem. The flux of mass through my surface is equal to a volume integral over the entire enclosed volume of the divergence of my vector field. This was Gauss. Okay. And so now I can take these two volume integrals and I can write them kind of all on one side. So this volume is taken, this integral is taken with respect to a volume, and I can bring my ddt inside that volume integral. So I get triple integral of omega of ddt rho plus rho div V d omega equals 0. Okay, so what did I do here? I just took this volume integral and this volume integral, and I brought this one over to the left-hand side so that this minus this equals 0. And now this is the integral form of conservation of mass. Okay, this is the integral form of conservation of mass. And this is a super useful general formula. But what's interesting about this is I didn't use any special properties of this volume omega. The only property I used about omega was that it was relatively nicely behaved and smooth. It could have been huge. It could have been really, really, really teeny. It could have been square or spherical or oblong. It doesn't matter. I didn't really specify anything about omega. So this volume integral of this quantity has to equal 0 for all omega. This is true for every omega you can name, practically, for every nice, smooth omega. And so the only way that that could possibly be true is if this integrand was equal to 0. Let me say that again. This volume integral is equal to 0 over every possible volume you could draw. You could draw that omega that I drew there. You could draw a little cube. You could draw any omega and move it around. And this quantity is still going to equal 0. And the only way that that could possibly be true for all of those infinitely many volumes is if this quantity on the inside was equal to 0. And so the only way that this can possibly be consistent is if ddt of rho plus rho times the divergence of V equals 0 everywhere. Okay, this is our first partial differential equation. This is a partial differential equation for mass conservation. This is called the continuity equation in fluids and elastics. And it's called a partial differential equation because I'm taking the derivative of p with respect to t over here and with respect to space over here. Right? I have partial x's and partial y's and partial z's. So we have a partial differential equation. And this is a linear PDE because first derivatives are linear operators, so this is a linear PDE. Okay, so Gauss's theorem can be extremely useful. These integral theorems in calculus are not just esoteric. They're not just, all of the problems that I'm going to give you, I made up some vector field that would be easy to solve. But in reality, the real use of these integral theorems is so that we can take conservation laws, conserved quantities, and write them as differential equations that we can solve on a computer, that we can analyze and start to really think about how does fluid move in a river? How does silt move? How does nutrients move? How does oil move in an ocean? And you always start with these conservation laws. Okay, that's where all of our physics equations start typically. You got a question?
Why you can bring the ddt inside the volume integral?
Right, so if I take and integrate my density over my volume, I get my total mass. Now I could take that total mass and I could say, what is the rate of change of that total mass in time? And it would be the same as saying, well, what's the change of little mass here, little mass here, little mass here, and integrating up all of those local rates of change of mass. So this ddt can go inside this integral because this integral is not with respect to t. And rho is not, at least right now, this omega is not changing in time. If omega was changing in time, then I would not be able to do that. But for a fixed volume omega, I can bring this ddt in. Okay, any other questions about this? Yeah?
So when you do the Gauss's theorem, why don't you put the rho in the divergence?
Okay, if rho is not a constant, then you're right. Then rho should be, I think, inside the... No, I think actually rho is outside. Yeah, I think you got to be right. It's got to be div dot of rho v. Yeah. Yeah. That makes more sense, right? Good. Yeah, exactly. If it's a constant, then it pops out. Yeah, all right, thank you. And if it's a constant, then ddt of rho probably also won't change. And then you'll just get the divergence of v has to be equal to 0. But that's fluid mechanics. Okay, so that's everything I have today. I think next time we'll talk about path integrals, contour integrals, and conservative vector fields. Thank you.